Welcome everyone to this AI Paper Podcast's Deep Dive. Today we're looking at some really interesting new work on sequence models.
Yeah, this is cool stuff. It basically proposes a new way to think about, almost all the sequence architectures we use.
Right, things like transformers, RNNs.
Yeah.
It tries to unify them.
Exactly. The core idea is viewing them as associative memories. And how they learn is driven by something they call attentional bias, kind of like cognitive attention.
And they introduced this framework, MIRAS, based on that idea.
That's the one. MIRAS breaks down model design into 4 key things: the memory structure, this attentional bias, a retention gate for how memory fades, and the learning algorithm.
Plus, they built some new models, Meneta, Memora, that seem to perform really well, even beating standard models on certain tasks.
Yeah, language modeling, reasoning, recall. Pretty impressive results, and they even talk about parallel training, so that's the quick overview for you.
Okay, great intro. So the paper it's all connected, a journey through test time memorization, attentional bias, retention, and online optimization. It's from researchers at Google.
Ali Berouz, Maisam Razavian, Pailan Zong, and Vahap Marekni.
And for you listening, especially if you're an AI researcher or ML engineer, our mission here is to really unpack this MIRAS framework. We want you to grasp how it connects these different models and what new design paths it might open up.
Yeah, hopefully giving you the insights to, stay ahead in this field. It moves so fast.
It really does. Okay, let's start with that first big idea. Viewing architectures like transformers and RNNs as associative memory modules. What does that mean in practice?
So think about basic memory. You get a cue, a key, and you retrieve a value, an associated piece of information. The paper argues that sequence models are essentially doing this.
They're learning a mapping from inputs, the keys, to outputs, the values.
Precisely. And the way they learn this mapping, the internal objective, that's what they call attentional bias. It's like the model's internal goal for making associations.
Okay, so this attentional bias is the driving force. Can you formalize that a bit?
Sure. So if M is the memory operator, mapping keys K to values V, the attentional bias L is the loss function that M tries to minimize. So M star, the optimal memory, is the argument minimum of LMKV.
Right.
And when the memory has parameters like weights W, you optimize over those parameters, potentially with some kind of regularization term, RW, which relates to memory retention.
And the surprising thing you mentioned earlier was that most current models use very similar biases.
Yeah, that's a key finding. Despite all the architectural variety out there, it often boils down to either dot product similarity, like in standard attention, or basic L2 regression, just minimizing squared errors.
That feels simpler than expected. If the core objective is often similar, what accounts for the differences in how models like, say, transformers and Mamba behave?
Well, that's where the other parts of the MIRAS framework become crucial. It's not just the bias, it's also about how they handle past information.
The forgetting part, or as they call it, retention regularization.
Exactly. They propose framing forgetting not as deletion, but as a form of regularization on an attentional bias objective. It controls how strongly the model holds on to past states.
So it's more about accessibility than erasure.
Kind of. And they prefer the term retention gate over forget gate to reflect this idea. It feels a bit more aligned with how we think about human memory. Sometimes things fade or become harder to access, not necessarily wiped clean.
That makes sense. So MIRAS brings together the architecture, the attentional bias, and this retention mechanism.
And the learning algorithm, those are the 4 pillars. So number 1, memory architecture. Is it a simple vector, a matrix, an MLP? Maybe something more complex, like their proposed memory mosaics. Figure 1 in the paper shows a few options.
Great. Architecture. What's number 2?
Number 2 is the attentional bias, the internal loss. Could be LP regression, dot product, Huber loss for robustness, KL divergence. Again, figure 1 lists examples.
Got it. And third?
The retention gate. How do you regularize to keep relevant memories? LP regularization, elastic net, KL divergence again, Bregman Divergence. Lots of mathematical tools you could potentially use here.
And finally, the algorithm.
Yep. Number 4, the memory learning algorithm. How do you actually optimize? Good old gradient descent, GD with momentum, Newton's method, maybe even non-parametric approaches. Figure 1 connects all these pieces visually.
This framework seems quite comprehensive. The paper also talks about 2 different viewpoints on how this learning and retention actually happens during training, right? FTRL and learning retaining.
Yeah, 2 ways to conceptualize the optimization process. First is the follow the regularized leader, or FTRL viewpoint. Think of it like online learning, step by step. At each step, the model chooses parameters that minimize the current loss. the attentional bias, but are also close to the previous parameters, controlled by a regularization term, the retention part. Equation 7 gives the math.
Okay, minimizing loss while staying stable.
Right. The second view is the learning-retaining viewpoint. This one emphasizes the trade-off more directly. Learn from the new data point, minimize attentional bias on current input, while explicitly trying to stay close to the previous memory state to retain past knowledge. Equation 8 shows this general form.
Are these views equivalent?
Not always. Proposition 3.2 points out that the learning-retaining view can actually be more general, especially if you use something called Bregman Divergence as your retention gate. It covers FTRL as a special case under certain conditions.
Interesting how it connects these high-level design choices to the nuts and bolts of optimization.
Absolutely. And it's not just theoretical. They show how existing models fit neatly into this framework. Table 1 is really insightful here.
What does Table 1 show us?
It maps models like RetNet, the transformer itself, Mamba, DeltaNet, Titans-LMM. It maps them all based on these 4 MIRAS components: memory architecture, bias, retention, and the learning update rule.
The takeaway was that many use similar core components, despite looking different on the surface.
Exactly. You see a lot of dot product or L2 bias and L2-like regularization for retention or forgetting. For instance, models like linear attention, RetNet, Mamba, GLA, they often fall under the umbrella of using dot product similarity bias with L2 retention. They're kind of like heavy in learning.
Yeah.
Then you have models like DeltaNet, Longhorn, RWKV7, which use more of a delta rule approach. MIRAS frames them as optimizing an MSE objective with L2 retention, often using SGD. That's equation 9.
What about transformers? How does Softmax Attention fit?
They actually frame Softmax Attention as a non-parametric solution, specifically using the Nadaraya-Watson estimator for an L2 MSE loss. It fits, but without an explicit retention term in the standard formulation.
And other models like Titans.
Titans-LMM, for example, uses a nonlinear MSE objective, and it has both local and global L2 retention learned with gradient descent plus momentum, so you can see the variety, but also the common threads.
This unified view is powerful. It implies we could get a lot of mileage out of exploring different attentional biases and retention gates, ones not commonly used.
Precisely what they argue. And they propose several new ones.
Like the LP attentional bias.
Right. Instead of just L2 squared error, why not use a general LP norm? Equation 10 shows this. This leads to different update rules, like equation 11. They even discuss a special case for valueless memory where values are just +1 or -1.
Does using P other than 2 cause issues, like differentiability?
Yeah, remark 5 touches on that. For some p-values, like p1, absolute error, it's not differentiable at 0. So they suggest using smooth approximations, which is standard practice.
Okay, what other novel biases did they explore?
Huber loss. This one's interesting. Huber loss is known for being robust to outliers, less sensitive than L2 loss to extreme errors. So using it as an attentional bias creates a memory with coping mechanism, as they put it.
More robust models, potentially.
Potentially, yeah. They show a few ones to apply it, leading to different update rules like equation 14 and 15, and even a smooth mixture approach in equation 16. They also looked at making memory robust to shifts in the value parameter itself, using ideas from robust optimization. This leads to a modified loss and update rule designed to handle uncertainty in the target values. Equation 17.
So moving beyond standard L2 opens up possibilities for robustness and different learning dynamics. What about the retention side? Did they propose new gates too?
They did. One idea is framing retention using divergences, like KL divergence, especially when the memory state is constrained to be like a probability distribution on a simplex. Equation 18 introduces this.
And KL divergence leads to?
Using KL divergence with Shannon entropy as the regularizer leads to an update rule involving softmax, shown in equation 21, so you get these nice probabilistic interpretations.
Interesting. Any other retention ideas?
Elastic net regularization. Borrowed from statistics, ElasticNet combines L1 and L2 penalties. Applied as a retention gate, it can induce both hard forgetting, setting some memory components exactly to 0 via L1 sparsity effect, and soft forgetting, shrinking others via L2. Equations 22 and 23 show this for the learning, retaining, and FTRL views, involving a soft thresholding operator.
So more fine-grained control over forgetting.
Potentially, yeah. They also briefly mention using general LP norms, for P between 1 and 2, for memory stability within the FTRL framework. And finally, Bregman Divergence.
Bregman Divergence. That sounds familiar from optimization theory.
Exactly. Using a Bregman divergence based on some strictly convex function, phi equation 24, as the retention gate leads to update rules that look a lot like mirror descent. They even give an example using the inverse sigmoid function.
Wow, okay. That's a lot of options in the design space now. Architecture, bias, retention, algorithm.
It really expands the toolbox, and to show it works, they built those 3 new models, Meneta, Yod, and Memora.
Right, let's break those down. What's Meneta?
Meneta uses that novel LP attentional bias, specifically with P3 in their experiments. And for retention, it uses a hybrid LQ-L2 gate with Q4.
And the memory architecture.
It's a 2-layer MLP with GELU activation and residual connections. Pretty standard building block, actually. Figure 2 shows it. Equations 24 and 25 detail the update and gradient calculations for this setup.
Okay, so LP bias, hybrid retention. What about Yod?
Yod is focused on robustness. It uses the Huber loss as its attentional bias. For attention, it combines local and global L2 regularization, similar to Titans in that respect. Same MLP memory architecture as Meneta. Equation 26 gives its update rule.
Makes sense. Huber loss for robustness. And Memora.
Memora goes back to a standard L2 regression loss for its attentional bias, but combines it with a novel retention gate. KL divergence. Again, same MLP memory architecture. Its update rule involves a softmax, naturally because of the KL retention. Equation 27.
So 3 distinct models, each exploring a different combination within the MIRAS framework, and they built these into larger models.
Yeah, they basically took a llama-style architecture and swapped out the standard attention layers with these MIRAS layers. They kept other modern components like MLP blocks with SWEGLU, rotary position embeddings, rope, and RMS norm. Figure 2 illustrates this overall backbone too.
How do they handle the parameters for the bias and retention parts, like the learning rates or regularization strengths?
They used channel-wise parameterization with low-rank projections for those learnable parameters, things like eta, delta, alpha in the equations. It's a way to keep the parameter count reasonable while still allowing flexibility.
And they also tried hybrid models.
Yes, combining MIRAS layers with some standard sliding window attention, SWA layers, that's also shown in Figure 2.
Now, a big challenge with recurrent models, especially nonlinear ones like these seem to be, is training efficiency. Transformers are easy to parallelize, but RNNs? Less so. How did they address that?
That's a crucial point. They used a chunking-based parallelization strategy. You divide the long input sequence into smaller chunks, say of size B. You process each chunk sequentially, but you can process multiple chunks in parallel across different devices. The key is how you handle the state dependency between chunks. They approximate the gradient calculations by essentially using the last hidden state of the previous chunk as the initial state for the current chunk, but without backpropagating gradients across the chunk boundaries during the parallel phase.
So it's an approximation, but it allows for parallel computation.
Exactly. Equations 28 and 29 show how this works for Meneta's LP loss, and equations 30-32 illustrate it for Memora with its KL retention. They mention that nonlinearities like the activation functions are often applied just at the end of each chunk within this scheme.
Clever. A practical way to train these otherwise sequential models faster. So let's get to the results. How did Meneta, Yod, and Memora actually perform?
They performed very well, actually. Table 2 compares them against baselines like Transformer plus B, various linear RNNs, and hybrid methods on standard benchmarks.
And kind of benchmarks.
Language modeling perplexity on datasets like Wikitext 103 and the Pile validation set, plus common sense reasoning tasks, PIQA, HelloSwag, Wiener Grande, ARC, Sevele, BullQ. Across different model sizes, 340 million, 760 million, 1.3 billion parameters, the MIRAS variants generally came out on top.
That's quite strong. What about handling long contexts? That's a big focus area right now.
Figure 3 addresses that. It shows scaling performance on the C4 dataset as context length increases from 2K up to 32K tokens. The MIRAS models generally show better perplexity scaling compared to baselines, especially at the 340M and 760M sizes.
And why is that?
The authors attribute it to the combination of their expressive MLP memory architecture and these novel attentional biases and retention gates, allowing them to capture longer-range dependencies more effectively. Figure 3 also plots perplexity versus FLOPs, suggesting better computational efficiency too.
Okay, so good on standard LM and reasoning, good scaling. What about tasks specifically designed to test long-range recall, like needle in a haystack?
They tested on that too, using the ruler benchmark's single NIAH task. Table 3 shows the results for context lengths from 1K to 8K. All 3 MIRAS variants significantly outperformed the baselines here as well.
Suggesting a larger effective context window.
Exactly. They seem better at finding that needle. Interestingly, Meneta did particularly well on a synthetic, noisy version of the task, SNIAHPK, which might point towards the robustness benefits of its LP bias.
That ties back nicely. Did they do any ablation studies to understand which components are most important?
Yes, figures 4 and 5 and table 4 show ablation results. Figure 4 looks at Meneta and varies the p-value in its LP bias. Performance seems best around p3, suggesting L2, p2 isn't necessarily optimal. Figure 5 varies the q in Meneta's LQ retention gate, showing that the retention mechanism does impact scaling behavior. And table 4 is an ablation on YOD, the Huber loss model.
What did the YOD ablation show?
It showed that removing the retention gate entirely hurts performance. Making the model input independent hurts performance. Removing either the L2 or L1 components from the Huber loss hurts, and using a simpler linear memory instead of the MLP hurts. Basically, all the key design choices they made for YOD seem to contribute positively.
That really validates the framework's components. It's impressive work, not just proposing a theory, but building models and showing strong empirical results, plus tackling the practical training aspect.
Absolutely. It ties together a lot of threads, associative memory concepts, cognitive science ideas like attentional bias, optimization theory, and practical deep learning engineering.
So wrapping this up, what are the main takeaways for the AI researchers and ML engineers listening? Why should they care about MIRAS?
I think the biggest takeaway is this unifying lens. MIRAS gives you a structured way to think about sequence models beyond just tweaking layer types. It encourages you to consciously consider the internal objective, attentional bias, and the memory stability mechanism, retention gate.
It's a more principled design approach.
Exactly. And the success of Meneta, YOD, and Memora proves that exploring beyond the standard L2 dot product biases and L2 retention can yield significant performance gains. It suggests there's a lot of untapped potential in designing these core components specifically for your task.
So it's a framework for innovation, really.
Yeah, it provides a roadmap for developing potentially more effective, maybe more robust, or more efficient sequence models. And the parallelizable training is a big practical plus. Understanding MIRAS can definitely spark new ideas for your own research or model development.
This has been super insightful. It feels like one of those papers that could genuinely shift how people approach sequence modeling.
It has that potential, I think. It connects things in a really elegant way.
For everyone listening, if this piqued your interest, we definitely recommend reading the full paper. It's all connected. There are more mathematical details, nuances on the parallelization, further ablations. It's rich.
Yeah, dig into it and think about your own problems. Could a different attentional bias help? Maybe a Huber loss for noisy data or an LP norm for different error sensitivity? Could a different retention gate like KL divergence or elastic net better capture the temporal dependencies you need?
That's the challenge, right? Applying these concepts, it really underscores this idea of interconnectedness, cognitive science, inspiring AI objectives, optimization theory guiding architecture. It's a fascinating space.
For sure. The journey the paper title mentions through memorization, bias, retention, feels like it's really just getting started, and frameworks like MIRAS are giving us better maps.
A great place to leave it. Thanks so much for breaking that down.
My pleasure. Always fun to talk about this stuff.
And thanks to all of you for tuning into this deep dive. We'll catch you on the next one.